Hello, in this video we are going to look at a magnificent piece of fluid dynamics, the Blasius boundary layer. So to set up the problem of the Blasius boundary layer, first of all let's just write down what the flow looks like. So we have a flat plate like this. I'm just going to make it slightly thick so we know what we're looking at, right? That this is our plate over which the boundary layer is developing. And there will be an incoming flow. So this flow is coming in from the left at a velocity capital U in the x direction. So this is the y coordinate, and this will be the x coordinate. Okay. And so that will be the origin of our axis. That's essentially the beginning, or the leading edge of this flat plate. And effectively, what will happen is that as the fluid encounters the plate, it's going to slow down here against the plate due to the no-slip boundary condition. But it still has to be at a capital U velocity, infinitely far away from it. So what will develop is a boundary layer which will have thickness delta x. It's a function of x. In that boundary layer we will see fluid velocity variations that go from capital U here to essentially 0 at the boundary due to the no-slip boundary condition. And just to give you an idea of what the flow can look like, we can look here at a certain distance, capital L, away from the leading edge. This velocity profile is going to look like this, where we have development of the streamwise velocity inside the boundary layer. And when we reach the boundary layer thickness, this delta x, then the fluid goes pretty much at the velocity it was going at away from the wall. Okay, so there is one assumption that we will make here, and this is the only assumption that is necessary to develop the theory for this Blasius boundary layer. And that assumption is that this boundary layer thickness is always small compared to the location where we'll look at, and I'll call that epsilon. So epsilon is small compared to 1. Okay, so what that means is that this height here is small compared to this. So we can imagine that if we're at a very large value of the Reynolds number, the flow is so fast that this boundary layer is essentially crushed down and remains very thin. This is what this sort of approximation translates. Okay, so now we have sketched and introduced some important quantities for the flow. We can start writing down the equations for this problem. So we're going to start with the two-dimensional Navier-Stokes equations. Navier-Stokes equation for and I'm going to look at a steady flow. I'm not going to look at anything too complicated. So that's just for a steady flow. Steady meaning d by dt equals 0. So what we have here is rho u du by dx plus v du by dy, and on the right hand side I'm going to get minus dp by dx plus mu d2u by dx squared plus d2u by dy squared. That's my first equation from the x coordinates, for the x components. Then I can write down the same Navier-Stokes equation projected onto the y coordinates. So this is u dv by dx plus v dv by dy equals minus dp by dy plus mu d2v by dx squared plus d2v by dy squared. That gives me my Navier-Stokes equation, and I need to solve, in addition to writing down these two equations, I need to introduce also the incompressibility constraint. So the incompressibility condition or constraint which in 2D writes du by dx plus dv by dy equals 0. And here I've got the three equations that I'm going to work with in this problem. 1, 2, and 3. Navier-Stokes and incompressibility condition. To complete this problem, we need to specify the boundary conditions. And, well, essentially, in this problem, we're dealing with a one-dimensional problem on y. We can't really specify boundary conditions in x. It would be a bit difficult as the flow is developing. So what we are going to write are the boundary conditions in y. And these boundary conditions are that the velocity has to vanish at y equals 0. This is translating the fact that we have a no-slip, a solid boundary, therefore no-slip boundary conditions apply. And in addition, if I look infinitely far away from this plate, I should recover the velocity, the incoming velocity, capital U, in the EX direction. Okay, so this is what I call the velocity at infinity. So the limit when y tends to infinity of u has to be equal to capital U, and the limit for y tend to infinity of v has to be equal to 0. So these are my boundary conditions, and the problem is formulated entirely here as a two-dimensional problem. Alright, to solve for this problem, what I think was Prandtl, Blasius' PhD supervisor back in 1900 or 1901, started off by proceeding to an asymptotic reduction of these equations and boundary conditions. So let's just have a look at what this asymptotic reduction involves. Well, let's just start off by non-dimensionalizing the equations as we're used to. And so let's just do x. And in x, let's say we're going to non-dimensionalize distances using capital L. Okay, so that's going to be capital L times x star. Well, where L is an arbitrary length, right? We have not said anything specific about it. Then in the y direction, we can non-dimensionalize things by the boundary layer thickness, which, remember, is a function of x. And because of this, we can actually get rid of this boundary layer thickness, or of the delta in there, but rather write it as epsilon times L times y star. Okay? So that would be the non-dimensionalization for the coordinates. Then u, well, for u there is a scale, which is capital U, so I'm going to use it. V, I do not know anything yet about V. I will know something soon about it, so I'll just write down V, capital V. And for the pressure, well, I'm just interested in a sort of kinematic approximation of it to make the Reynolds number appear in front of only the viscous terms, which is what we typically do when we have large Reynolds numbers. So what I'm going to do here is non-dimensionalize the pressure by rho u squared, and this is what was done in Prandtl's work back then. Okay, so based on this non-dimensionalization, I can just have a look at the incompressibility condition, and very immediately what I get is that it turns into u over L du star by dx star plus v over, I can write delta or epsilon capital L dv star over dy star equals 0. And the trick here is that I want to preserve the two-dimensionality of my flow. Therefore, I do not want to get rid of either term. So what I need to have to preserve this balance is u over L has to be equal to v over epsilon L. In other words, to preserve that two-dimensionality in the flow, what I need to impose is that v is epsilon capital U. V is epsilon capital U. So the velocity in the vertical direction, or pseudo-vertical direction, has to be small compared to the velocity, the streamwise velocity, okay, along the flow. Good. So that gives us this approximation here, so we can just fill this out here. That will be epsilon capital U V star. Okay. And now we should have a look at what the Navier-Stokes equations become. So let's have a look at one, proceeding in order. So I've got U here, so that's going to be rho U squared over L times U star d U star by dx star. My first term here. The second term, there will be an epsilon coming from the V, but 1 over epsilon coming from the d by dy. So they cancel out. I get rho U squared over L V star du star by dy star. And on the right hand side, my pressure is non-dimensionalized by rho U squared, so I get minus rho U squared over L dp star by dx star. And my diffusion operator here leads me to write mu U over L squared d2 U star by dx star squared. And the second term involves y in the denominator, therefore I'm going to have a 1 over epsilon squared. So that's mu U over epsilon squared L squared d2 U star by dy star squared. Okay, so that is my equation for the x component of the Navier-Stokes equation. What I need to do now is to simplify this a little bit. So I'm going to divide everything by rho U squared over L, so that the left-hand side has no prefactor. So that's going to be U star d U star by dx star. Then I'm going to have plus V star du star over dy star. On the right hand side, well, this is the same prefactor, so in front of the pressure I have no coefficients in front of the gradient of pressure, so it's dp star over dx star. And then here what I get is the inverse of the Reynolds number, so I'm getting plus 1 over REL, the Reynolds number based on that length capital L, which I haven't yet said anything about. So that's going to be d2 U star by dx star squared. And this second term is very similar, but it has an epsilon squared in the denominator. So I'm getting this d2 U star by dy star squared. So this is my first equation. My first equation turns into this. Let's do the same thing for the second equation. So the second equation gives me that we have rho, we're going to have an epsilon due to this V, so rho U squared epsilon over L, U star d V star by dx star. Then I'm getting 2 epsilons in the numerator, 1 in the denominator, so I'm going to have the same prefactor. So that's V star dV star by dy star equals my pressure gradients minus rho U squared over, this time is by y, so I get epsilon L here, dp star by dy star plus my advection operator here, my diffusion operator here, so mu U epsilon coming from the V over L squared d2 V star by dx star squared. And the second guy here is mu U, I should have an epsilon in the numerator but 2 in the denominator, so epsilon L squared d2 V star by dy star squared. And in a similar fashion to this equation, I'm going to divide everything by rho U squared epsilon over L, so that the prefactor of the left hand side is unit. So that's U star dV star by dx star plus V star dV star over dy star equals, So here I'm getting 1 over epsilon squared in front of the pressure, 1 over epsilon squared, there's a minus sign, dp star by dy star, and then here I'm getting just 1 over the Reynolds number, times d 2v star over dx star squared, and here I'm getting 1 over epsilon squared times the Reynolds number d2v star over dy star squared. Okay? So this is our first reduction of these two equations to these non-dimensional forms. I forgot to write down for these two equations that we had introduced that the Reynolds number based on the length L is rho u L over mu. Okay, or yeah, I didn't introduce the kinematic viscosity here. Okay, so now we have reduced these equations. There's a couple of things that we can do there. First of all, what we want to notice here is that because epsilon is a small parameter, this is going to be large. 1 over epsilon squared is going to be large. So this term is going to dominate over this term. So diffusion in the diffusion in the wall normal direction dominates over diffusion in the streamwise direction. And as a consequence, I can, as a first order approximation, get rid of this guy. And also, this is also true because we're interested in large Reynolds numbers, so this is always going to be small, and therefore that term is never going to dominate over advection. Okay? So it's smaller than advection, and at the same time it's smaller than the largest term in the diffusion operator, therefore we're just going to get rid of it. The similar reasoning can be applied here, and so we can get rid of this term. And based on this, then we're left with one other question, okay, which is what's the balance in these equations. First of all, if we look at this equation here, this is order 1, so we're happy. There's no problem with that. This is order 1 over epsilon squared, so this is actually large. So the gradient of pressure in the wall normal direction in this equation dominates over advection. Okay. And then this is 1 over epsilon squared times the Reynolds number. So the Reynolds number being large, this is always going to be smaller than this. And so in this equation, this is the gradient of pressure that always is going to dominate. Because we're always saying that in this calculation that epsilon is small compared to 1 and the Reynolds number is large compared to 1. So based on that, there's no other possibility in this equation than this term dominating. Okay, so this equation is not going to carry a lot of physics so far. Let's have a look at the other one. So this is order 1. We're happy with that. This is also order 1. That's excellent news. And what we have here is an additional term. So 1 over epsilon squared is large. Okay? So either the Reynolds number is too small, that this term is still large, but then in that case we lose advection and the pressure gradient, but we lose advection more importantly. Or the Reynolds number is sufficiently large that we can compensate and this term balances with the rest of the equation, in which case we can keep everything. The third possibility is the Reynolds number is so large that this is actually small compared to 1, and therefore the flow is just dominated by advection. In this case, this would be boring, because if the flow is dominated by advection, we would barely have any boundary layer, and we're interested in this boundary layer particularly. Okay, so there is only one solution for us, so that this term balances the rest of the equation, so that diffusion and advection are in balance. We impose that epsilon squared times the Reynolds number be equal to 1. Okay, and so you can rephrase this by saying that the Reynolds number is equal to epsilon to the minus 2. That's one way of rephrasing this. Or you can say that epsilon is the Reynolds number to the power minus 1/2. Okay? And that essentially gives us an idea of where we're looking at in this direction, right? So the Reynolds number was involving that distance, capital L. So you can essentially put the slider along the flat plate here at the location where you can strike this balance. So that boundary layer that we're calculating here is going to be valid at a certain distance away from the trading edge, but not too far away either, in such a way that we have this balance. Okay, so provided that we have now this balance, that we've established this balance, so let us recap what equation. So that we'll just write down this as being 4 and this as being 5, and we'll recap what equations we have. So system, so that's 3, 4, 5 now. 3, 4, 5 becomes, so system 3, 4, 5 becomes, I'm rewriting 3 in non-dimensional variables, but because I've written this down here, because of this balance, both terms remain. So I'm getting du star by dx star squared, dx star plus dv star by dy star equals 0. 4, remember this is 1 now. So 4 becomes u star du star by dx star plus v star du star by dy star equals minus dp star by dx star plus d2u star by dy star squared. And 5 just involves this dominant term, so that's dp star by dy star equals 0. So that's the system that we have to solve now that we've made some asymptotic predictions. Assumptions, sorry. So, since dp by dy is equal to 0, that means that the pressure doesn't change depending doesn't change with the distance away from the boundary. And because that is so, we can just express the pressure very close to the wall by just calculating what it's equal to very far from the wall. And very far from the wall, there's no viscous effects that occur, and the flow is essentially potential. So, since dp star by dy star equals 0, we can determine the pressure close to the wall by calculating it at a large distance away from it. And as I say, away from the boundary layer, the flow is potential, and we can apply the Bernoulli equation. The Bernoulli equation for a y equals constant streamline. And that equation writes p plus rho u squared over 2 equals constant. So that's a constant along the streamline. I'm not going to write down what that constant is. This is not going to be impacting our calculation. So if I non-dimensionalize this equation in the same way as I've non-dimensionalized the rest, I'm getting rho u squared p star plus rho u squared u star squared over 2 equals constant. In other words, if I divide everything by rho u squared, which is a constant, I'm getting p star plus u star squared over 2 equals constant. And then let's just think about it for a second. What is u far away from the boundary? Far away from the boundary, we know that u is capital U. And we've non-dimensionalized u by capital U. Therefore, this u star is actually 1 far away from the boundary. So this is actually 1/2, which is also a constant. And that means, in other words, that p star is a constant. What we get out of this, and that's going to become very important in a second, is that dp star over dx star is 0. And if that's valid far away from the boundary, because dp star by dy star equals 0, then that is certainly true in the very close vicinity of the boundary. And so we can just simplify this equation here by removing this term. All right? So, in other words, the system that we have, which was quite complicated in the beginning, starts to become a little bit more tractable. So what we have is our system becomes we still have this incompressibility condition. So du star by dx star plus dv star by dy star equals 0. Then that equation remains the same except for that term that disappears. So we have u star du star by dx star plus v star du star by dy star, and that is going to be equal to this double derivative. So d2u star by dx star squared. And well, since we've just gotten rid of the pressure, there's no need to add this equation. It's just not going to help us at all here. So that's it. That is our system. We reduced our system, which was kind of incredibly complicated in the beginning. There was a pressure, there was plenty of derivatives in all sorts of, plenty of non-linear terms, 3 equations, 3 unknowns, to 2 equations, 2 unknowns, right? So that is a bit more tractable. Yes. Okay, so we can, well, that's what Prandtl was doing back then. He was always working in dimensional form. So let's just we can rewrite down the system in non-dimensional form. So in dimensional form. So in dimensional form, this is du dx plus dv dy. That is 0. This becomes, we will have a rho in front of all this, and then there will be a mu here, but I'm just going to divide everything just to have one less quantity to worry about. So that's going to be u du by dx plus v du by dy, and that's going to be equal to mu over rho, so mu d2u by dx. This is going to be a y. This is a y. dy squared. Okay? So that's what our system becomes. The flow is two-dimensional and is incompressible, so we can introduce a stream function. Let us introduce the stream function. Stream function psi, and that stream function definition is going to be that u is d psi by dy and v is minus d psi by dx. And well, introducing this stream function has the very nice advantage that while the incompressibility condition is automatically satisfied, so we get rid of one equation, and what we have is this equation then. What is the notation here? We're at 6. 6 becomes, and then 6 becomes d psi by dy times d psi, d2 psi by d. Following on from this equation, Blasius made a very important assumption, and he said that the boundary layer was self-similar. In other words, what that means is that the boundary layer, this profile, okay, is always going to be looking the same at various locations along the flat plates, except to a stretching factor. in the wall normal direction. And that turns out to be a very powerful approximation mathematically, as you will see in a second. It helps bringing this equation. So this is an equation for one function, psi, the stream function, but it's posed on a two-dimensional domain, which is y and x. Okay, and so that self-similarity hypothesis is going to bring us from this two-dimensional domain onto a one-dimensional domain, as you will see in a second. So this is from Blasius. I think it's 1903. So the boundary layer can be thought of as self-similar. In other words, its profile will be identical to a stretching factor along the flat plates. Okay, and mathematically, the way to write down this approximation is to introduce a self-similarity variable, which we call eta here, and eta will link y and x. The way that Blasius did it is by writing y times u over nu x to the power 1/2. Okay, and we'll introduce this thing here. This group here will be introduced as 1 over gamma, and so that's going to be y over gamma, where gamma of x is nu x over u to the power 1/2. So this is going to come in very handy in the development of this calculation. And so that's one hypothesis here. And then what he also wrote was that the velocity u was non-dimensionalized using capital U, but then it was, remember, u depends on x and y. It was a function of eta differentiated with respect to eta. Okay, and the reason why he said this for u is because, of course, what we're interested in here is not u and v, but rather psi, because from one function we can get back to the two components of the velocity. And u being a differentiation, being the stream function differentiated, then that's why he introduced the prime here. So that when we go back to psi, well, we don't get f prime, but we'd rather get f. So let's just do this calculation for here. So the definition of the stream function implies so that implies that u f prime of eta equals d eta psi dy eta, right? I'm just writing down this, but using these new variables. So u f prime on the left hand side, and d psi by dy is d psi by d eta by dy. And I just realized I changed notation here. I apologize. I tend to use that sort of notation when I have long calculations ahead. So this is d psi by d eta, or d sub eta times psi. Okay, and then based on that, then we can integrate psi, and psi is equal to u, which is a constant, times the integral from 0 to eta of f prime eta divided by d eta by dy, and this is integrated with respect to eta. And therefore, what I can write is that psi is u d eta by dy is 1 over gamma. So the gamma comes back up, and gamma doesn't depend on eta, so gamma comes out. And then the integral of f prime is just going to be f of eta. Okay? So that simplifies enormously the expression of these functions by essentially writing down that psi now is u gamma f. Okay? And another quantity that we'll be needing in what follows, in the calculation that follows, is that we have d eta by dy, which is trivially 1 over gamma, right? What we also need is d by dx of eta, okay? And so d by dx of eta, or I can take this with gamma depending on x. D by dx of eta is y d by dx of gamma to the minus 1, or minus y gamma prime d by dx here of gamma over gamma squared. And then these quantities are going to become, these calculations are going to become important in the development of this calculation. Okay, so with all these calculations in mind, what we should be doing now is trying to turn this equation into an equation for psi, but over the quantity eta rather than x and y. So before doing that, what we need to express are all the derivatives from this equation. So first of all, let's just try and have a look. So let us express all the terms in or from equation 7. So first of all, the first the first of these terms is d by dx of psi. Okay, so that's this term here. So d by dx of psi, if we take psi to be this function here, d by dx of psi is going to be u d by dx of gamma times f plus u gamma d by dx of f, which is d by d eta of f, d eta by dx. Okay, and by at the same point we should notice that this quantity here, d by dx of psi, is minus the velocity in the wall normal direction. So that's minus v. Just to notice this here. So that leads us to write down that this is u, and gamma is a function of x only, so I'm just going to write down this as gamma prime f. And the second term here, we need to differentiate eta with respect to x, which we have just done here, and it gives us minus y gamma prime over gamma squared. So I'm getting minus u y f prime gamma prime over gamma. Okay, so that is my first term. That is my first term with that I'll be using here. Well, my first differentiation term that I'm going to be using. Then we need to find out these differentials with respect to y. So let's just have a look at d by dy of psi and d by dy of psi. Psi is still given here. But the only term that depends, the only function that depends on y here is f through eta. So it's u gamma, and I'm going to have d by d eta of f, d by dy of eta, and d by dy of eta is just 1 over gamma. Okay, so what that gives us is u gamma, it's 1 over gamma, so it's actually going to simplify, f prime 1 over gamma, that is to say u f prime. And what we should also add here is that this quantity is directly the velocity in the streamwise direction. Okay, so that is what we have here. Then we can continue and write down dy y of psi, or dy squared of psi if you want, which is the differentiation of this quantity with respect to y once more. And so, in other words, we're going to get a second d by d eta here, dy by d eta. So we're just getting f double prime 1 over gamma. So it's u f double prime over gamma. And in a similar fashion, we can get the third the third order differentiation here, which is going to give us u f triple prime over gamma squared. Okay? And there is one last term that we need to find. So we've got that one here, we've got that one, we've got that one, we've got that one. This is the last one that we need. So it is dx y of psi. And to get dx y of psi, I'm going to take dy of psi here, and I'm going to take the x derivative of this. So u is a constant, so I'm just getting the u out here, and this is going to be d by dx of f prime. In other words, it's u d by d eta of f prime, so that's f double prime, d eta by dx. And d eta by dx, we've got it already done, it's in here, so we can just plug this back in, and that gives us minus u f double prime y gamma prime over gamma squared. Okay, so all these terms expressed. And with all these terms expressed, now we can take equation 7 and plug everything in. So equation 7 gives us that we should have d by dy of psi, which is this guy, so it's u f prime, times this term, which I've just calculated here, so it's minus u f double prime y gamma prime over gamma squared. Then we will have minus d by dx of psi. D by dx of psi is expressed here. So that gives me u gamma prime f minus u y f prime gamma prime. This is over gamma times the second derivative of psi with respect to y, which is here. So that's time u f double prime over gamma. And on my right hand side, I'm getting nu times the third derivative, which is here. So nu u f triple prime over gamma squared. So that is my equation expressed in these new quantities. So let's just develop all these terms here. So here we get minus u squared f prime f double prime y gamma prime over gamma squared. This first term here gives me a minus sign again. I get u squared f double prime gamma prime over gamma. And this third term, there's a plus that comes in, gives me u squared f prime f double prime y gamma prime over gamma squared. And on the right hand side I get nu u f triple prime over gamma squared. And at this stage we can notice that this term and this term are the same. So these guys go away. And then all we have left are these two terms. So I'm going to just group everything with f triple prime on the left hand side. So I've got nu u f triple prime over gamma squared. That guy comes here, so I've got plus u squared f double prime gamma prime over gamma equals 0. I can of course simplify this a little bit by dividing everything by nu u over gamma squared to give me f triple prime plus u gamma prime, f double prime, and this is over nu, and that is equal to 0. And here we need to think about it for a second. We want to finalize this equation, and to finalize it we need to figure out what this group here is equal to. So let us just, so I'll call this 8. Let us just go back to gamma. So let us remind ourselves that. So gamma, where did we write gamma? Gamma is here. So gamma is nu x over u to the 1/2. What that means is that I can take the x differentiation, I can differentiate that with respect to x and get that the result is 1/2 of nu over ux to the 1/2. So I can multiply both guys there, and if I multiply gamma with gamma prime, what I get is 1/2 coming out. The x simplify, and I'm getting nu over u. Okay, so effectively I can replace this here, and what that gives me is that the nu simplify with this one and the u simplify with this one, giving me only the 1/2 coefficient. So 8 here becomes f triple prime plus 1/2 of f double prime equals 0. And this is already a much nicer equation to solve than, if you remember, the original problem, which was a set of three nonlinear system of 3 equations on 3 quantities posed on a 2-dimensional domain with very difficult boundaries to assess. Well, this is just a 1-dimensional problem for 1 quantity. And I haven't expressed the boundary conditions here, but let me just express the boundary conditions. Boundary conditions. So, well, the boundary conditions here, they used to involve u and v equals 0 at y equals 0. So u equals 0 at y equals 0 means f prime equals 0 at y equals 0. Okay, y in here we've used that change of variables, so it's got to be eta equals 0. Okay, so it's f prime equals 0, eta equals 0. Then we need to have also v equals 0 at y equals 0, so at eta equals 0. V equals 0 is this quantity here. So if f prime is equal to 0, that means that, well, f equals 0. So f equals 0 at eta equals 0. And, well, this is a third order problem, so I need another, but only one more boundary condition. And that boundary condition is the one provided by this limit here, which is that the limit when eta tends to infinity, or y tends to infinity, of this is f prime has to be equal to 1. Okay, remember the definition of u here. Okay, and that is the problem that Blasius reduced, that Blasius obtained when he reduced this Navier-Stokes problem using the self-similarity condition and this asymptotic reduction. A much simpler problem to solve for than the full Navier-Stokes problem. This concludes this video on the Blasius boundary layer.